Okay, in section 14.7, we're looking again at triple integrals using spherical coordinates. We have a triple integral with a Q here, where the bounds would denote a solid region of some function of x, y, and z dv. When you convert this to spherical coordinates, you replace every x with rho sine phi cosine theta, replace every y with rho sine phi sine theta, and replace z with rho cosine phi, and replace the differential volume dv with rho squared sine phi d rho d phi d theta. And then you would determine your bounds for rho, for phi, and for theta. If this is a triple integral without a function of x, y, and z before the dv, if it were simply a triple integral dv, that would give you the volume of the region Q. In this example, we want to find the volume of this solid region that's bounded below by this cone z squared equals x squared plus y squared, and above by the sphere. So the bottom of this region is the cone, the upper portion of this cone, z squared equals x squared plus y squared. Sort of like looks like this little ice cream cone around the positive z-axis. And above the top of that region is the sphere of x squared plus y squared plus z squared equals 9. We are going to be looking at determining bounds for our rho, the distance from the origin out to the points, and those are going to be points on that sphere. And we also want to look at our bounds for phi, where phi is the angle from the positive z-axis all the way out to here, whatever that angle is, where this cone intersects the sphere. And where the cone intersects the sphere is where the z on the cone is equal to the z on the sphere. So we're going to have to be solving some equations to determine that angle phi, which goes from the positive z-axis out to where they intersect. And then we also want to determine our bounds for theta, and theta would go from 0 in this case to make that complete portion there. The bounds for theta would go from 0 to 2 pi. Now in spherical coordinates, the equation of the sphere, there is a conversion equation. X squared plus y squared plus z squared is equal to rho squared. So that equation of the sphere can be simplified to rho squared equals 9. So that means rho equals 3. Our bounds for rho would be from that point, the bottom of that cone shape, out to the rho equals 3. And then if you want to determine where the sphere intersects with the cone, you can set, you can do that substitution here. If we know that the x squared plus y squared equals z squared of the cone, you're going to plug that into the equation of the sphere, and you get z squared plus z squared equals 9. Again, this was our equation of the sphere, x squared plus y squared plus z squared equals 9. And in the cone, it was z squared equals x squared plus y squared. So we're going to replace the x squared plus y squared with the z squared. Now we can simplify that to get 2z squared equals 9, or you can divide by 2. You get z squared equals 9 over 2. And then when you take the square root, you get z equals 3 divided by the square root of 2. If you rationalize that, that z equals z is going to equal 3 square root of 2 over 2. And to determine the angle phi, you use the conversion equation z equals rho cosine phi. If you replace the rho with 3 that we got there, and the z with 3 divided by square root of 2, you get this, and divide by rho, we get 3 square root of 2 over square root of 2 times 1/3 is equal to the cosine of phi. This can be simplified. Divide out those 3 and get 1 over square root of 2. And if you rationalize that, you get the square root of 2 over 2. So that means your angle phi is pi over 4. So that angle phi is going to go from the positive z-axis angle of 0 out to where the cone intersects the sphere at pi over 4. And then you can use the integration order d rho, d phi, d theta, where the bounds for rho go from 0 to 3. Again, looking back at the picture, okay, and again, that rho would go from that tip of the cone out to the sphere, and that sphere has a radius of 3, so rho goes from 0 to 3, while the angle theta goes from the positive z-axis down to pi over 4, and the angle theta goes from an angle of 0 all the way around to pi. So the triple integral for volume of a region Q is a triple integral of Q dV, and when converting to spherical coordinates, the dV is replaced with rho squared sine phi d rho d phi d theta. And our bounds for rho, the inside differential is d rho, where rho goes from 0 to 3. The next bounds are for phi. Phi goes from 0 to pi over 4, and then theta goes from 0 to 2 pi. When you take the antiderivative of the inside with respect to rho, you treat rho as the variable and phi as a constant. That's going to be rho to the third power over 3. And then when you plug in rho equals 3 and rho equals 0 and simplify, you get 9 sine phi. You integrate the inside integral with respect to phi and evaluate it at the bounds. And then you get a single definite integral, and you can evaluate that to get an exact answer, or you can use the integration feature on a graphing calculator to get a decimal approximation, which is approximately 16.569. So that value is the volume of what is inside the sphere, bounded above by the sphere and bounded below by that cone.